Hope everybody's off to a good start to their day. We've got a whole whopping 2 people on the stream. Galgoya, excuse me, and Willie. How you guys doing this morning? Um, all right. Well, so let's get to it. Um, Wanted to start with just kind of a recap of the geometry of what we were doing. So let's um, go back a couple of pages to here. There. Okay. So um, we um, we had two techniques for approximating integrals, the left-hand and the right-handed rectangle versions. Um, and this parabola example, we'll return to it. And realize that there's maybe a couple other ways we could do it. So, um, with this parabola example, what we discovered was that the left-handed rectangle version um, was an overestimate because the rectangles were always above the curve, and so we had too much area. The red ones, which were the right-handed version, were always below the curve, so they were a little bit too small. And so in kind of the, Goldilocks spirit, one of them was too big, one of them was too small. Is there a way that we could get a better approximation? Um, and one answer that you might suppose is, well, why not just average the two? Um, if one's too big and one's too small, then the true answer is somewhere in between. The average would be probably closer to the true answer than than it would be otherwise. Okay, so in this case, the 17 force and the 25 force were our two answers. Okay, so let me go back over here to a new page. Okay, so um, we considered uh, this. We found that the left-handed version was 25 force, and the right-handed version was 17 force. Okay, so the L4 and R4 here stand for left versus right hand rectangles, and then the 4 just indicates how many of them we used. So, right. Um, so if we average these, if we average them, then what do we get? So 25 plus 7 is 32, 42 over 8, which would be 21 over 4. Okay. Um, Now, as a decimal, um, that's just what, 5 1/4. Um, and the true answer, um, the true answer. Um, so compare the true answer that we found was 16 thirds, which is about 5.3. Well, 5.3 repeating. So um, so this is a lot better of an approximation by just averaging the left and the right hand methods. And this average method is called the trapezoid rule. And the reason for that, so let me kind of sketch the picture again. So we had 0 to 2, and this is up at 4, and so our parabola would look like that roughly. Um, so let me kind of just sketch in, I'll sketch in one rectangle. Okay, so this one, this would be the left-handed version that was too big. Um, well, okay, actually, let me back up because, yeah, okay, so let me just draw in sort of a 1 unit wide rectangle here. That would be the left, or the left-handed version, which was too big. This would be the right-handed version, which is too small. And if I average them, then effectively what I'm doing is I'm saying connect this point and this point with a straight line and compute the area of the green trapezoid. Okay, so does that make sense that um, why averaging them is equivalent to computing the area of the trapezoid? Does that make sense? Are we Gucci? We Prada? Oh, look, good. Everybody else is here. Uh, hopefully, yeah. Um, okay, so now in this case, looking at our picture, um, in this case, the T4 or trapezoid 4 would be an underestimate, and the reason is that because our curve is concave down, then um, so if we have a concave down curve like this, and I connect 2 points with a straight line, the straight line is always going to be below the curve. And so hence the trapezoid is going to miss this little chunk of area there. It's not a very big chunk, but it's still going to miss something. Um, so while it's an underestimate, it's a whole lot better of an estimate than, say, the right-handed method in this particular case. It's less of an underestimate than the right-handed method, and the left-handed method was an overestimate. So it's sort of splitting the difference, if you will. Okay, so there is another way that we could do this, and so I'll need to sketch a new picture for that, um, which is we could have instead said, all right, if I want to do a rectangle that's 1 unit wide, right, then what I could do is rather than taking its height to be given by the left-hand end or the right-hand end, what about if I use the middle of it? Okay, so this is called the midpoint rule. Oops, that looked terrible. Um, the midpoint rule. Okay, so there what we're going to do is, let's say that I make my intervals 1 unit wide, so 0, 1, 2. I'm going to pick the midpoint of each subinterval and use that. So let's pick a different color. Here, why don't we use orange? Okay, and so my two rectangles would look um, like this. Okay, so the idea there is that um, we uh, we underestimate with respect to, say, that little sliver there, but we overestimate with respect to that little sliver there. And again, it's sort of, well, it's going to partly overestimate, it's going to partly underestimate, and so maybe roughly those would sort themselves out. Okay, so let's actually compute this. This would be a picture of um, M2 because I only drew two rectangles. Um, but let's compute this for, say, 4, and let me sketch sort of the picture there a little bit bigger. This will hopefully help us. Um, okay, so the half points, or I'm sorry, would help if I could do fractions this morning. This would be 1/4, 3/4, 5/4, and 7/4 would be the middle points. And then, so I would have here, and the height would be there, and then this one would be here, and here, and there. Okay, so if we add all this stuff up, what are we going to get? What we're going to get would be, so M4 would be, well, the width of each rectangle is still 1/2 unit. Okay. And then the heights are going to be given by the function at 4 places, like so. Okay, so then all we have to do is compute those because we know that the function is the same function that we've been using for sake of example. It's this thing. Okay, and so let me Mathematica it real quick. Um, oops. And in fact, I'll go ahead and switch over to Mathematica on the screen here, uh, so you guys can see what I'm doing. All right, so let me make the font a little bit bigger. All right, so we have our function is 4 minus x squared, and I wanted to compute 1/2, which is the width, times the sum of f of 1/4, f of 3/4, f of 5/4, and f of 7/4. And, uh, oh, God, I'm an idiot. Sorry. You have to use square brackets. It's definitely too early, and I have not had any coffee yet, so. Okay, there we go. So we get 43/8, which is approximately uh, 5.375. Okay, so there, we're good. All right, so let me go back to the iPad. And so there we go. 43/8 was the sum, or 5.375, which is pretty dang close, right? It's a slight overestimate um, uh, compared to the true answer, which was 5 and third. But that's not too horrible. So um, yeah. Now, I want to make clear that the midpoint rule and the trapezoid rule are two different rules. So they both involve averaging. The question for each of them is when you average. The trapezoid rule, you average after you take the answer or you get the answers, right? So it's the left hand, right hand average. The midpoint rule, you're using the average of the x coordinates. So this would be the midpoints, 1/4, 3/4, and so on. And then you plug those in. And if the function is anything other than a linear function, then those two answers are going to be different. They'll be close, but they're not the same thing. Um, okay. Um, so the book actually does not mention the midpoint rule, or sorry, the trapezoid rule. It does mention the midpoint rule, um, but since the trapezoid rule, really you can just get that by um, averaging the left and the right hand methods. It's not really necessarily a new rule. Um, yeah. Okay. So anyway, so that's the midpoint and trapezoid rules. And like with the left and the right-handed methods, you certainly can make your approximations more accurate um, by using more rectangles or trapezoids, depending on which method you're going with, right? So the more rectangles or whatever you use, the better the approximation is going to be, and basically the only limit on this is how much work you want to do. Um, so that brings us to an important point for the sake of the homework, which is when you guys are doing these things and getting numerical approximations, you need to be very careful with your arithmetic and, in particular, very careful with your rounding. Um, if you round intermediate answers, then you're going to be basically adding up a bunch of stuff that's inaccurate, and that's going to make it even more inaccurate. So, um, what I would suggest is basically try to avoid rounding at all until the very end of the problem. And if you are sort of forced to round, go out to like 5 decimal places or something kind of ridiculous. Um, just to avoid numerical error. So, it could be the case that your answer is, or your setup for the problem is right, but you just rounded too much, and then that's going to throw you off, and then you'll not get it correct. Um, so, um, yeah. Okay. So next, let's go on to kind of the one of the central aspects of calculus. Um, and so let's go over to a new page. Okay, so let's talk about the fundamental theorem of calculus. And there are two sort of versions of the fundamental theorem of calculus. Um, and we'll sort of call them part one and part two. Um, I'm actually going to start with part two just because I think it is maybe a little bit more intuitive to start with. And so let's return to uh, the question that we've been working with, namely that we had that definite integral, integral from 0 to 2 of 4 minus x squared, and we got 16 thirds. Okay, so we did that using the Archimedes trick because this was a parabola. But if that had been 4 minus x cubed, or some other non-parabolic function, that trick wouldn't have worked. And so then the question is, then what? So here's sort of um, the the wonderful thing about calculus. Um, what is the antiderivative of 4 minus x squared? So what's the antiderivative of 4 minus x squared? And you can type it in the chat or type it in the Discord chat or speak it out to me. Anybody? Do we remember antiderivatives? No, it's been a little while. Yeah, 4x minus, well, it'd be x cubed over 3. Um, so it'd be 4x minus x cubed over 3. And then technically we have the plus c. I can, as we'll see in a moment, we can ignore the plus c in this situation, but we'll see why. Um, but okay, so we get this antiderivative. All right, wonderful. So let me call this fatty f of x. Okay, just to give it a name. And then I have two numbers there, 0 and 2. So what I'm going to do is, what is f of 2? Well, this would be, uh, sorry, this would be 4 times 2 minus 2 cubed over 3, which would be 8 minus 8 thirds. Okay, whatever that is. And f of 0 in this case, oh, I'm sorry, I forgot the plus c. Let me add that in. And f of 0 in this case would actually just be 0 minus 0 plus c, which is just c. Okay. And that's just because of the function in particular here was, um, yeah. So then what I'm going to do is I'm going to subtract one from the other. And in this case, um, one of them happened to be almost basically 0. But what I would get would be 8 minus 8 thirds plus c minus 0 plus c. And so the plus c's actually cancel. This is why in this situation I could have blown it off. And I would just get 8 minus 8 thirds, which is 16 thirds, which is exactly what we got when we did it with the Archimedes method. So, that's pretty cool. So this gives us another tool to solve these problems. Okay, so let's state this in general. Then we get this. Okay, so if you have an antiderivative of the thing you're integrating, then all you got to do is plug in the top number, the b, plug in the bottom number, the a, and subtract the two, and that gives you your answer. Okay, so one thing I want to point out is this may seem too easy. Um, Once you've found the antiderivative, then it's easy. It's just a matter of some arithmetic. The thing that's hard here, and we'll see this in spades probably starting Friday, is finding the antiderivative in the first place. Okay. Now, if we look back up at the previous example, um, it wasn't too difficult to find the antiderivative of 4 minus x squared. That wasn't that bad. Um, but if the function were a little nastier, or had a whole bunch of more stuff going on, then the antiderivative finding step could be the problem. Okay, and that is generally where the problem is going to be. Um, okay, so what this this theorem means is um, that, and it may be sort of surprising in a sense, right? That we have this idea of anti-differentiation, okay, which we got by saying, well, we can do derivatives, so if we can do derivatives, then we can do antiderivatives. Fine. Um, Separately, we have this idea of the integral, which is sort of this assignment of signed area. And at first glance, there's no reason to suspect that those two things have anything whatsoever to do with each other. And what makes calculus so neat, or what makes this theorem so amazing, is that it says that the two actually are very deeply related. That area and antiderivatives really do go together um, in a way that perhaps you wouldn't have thought would have been the case from the get-go. Okay, so there you go. This is the fundamental theorem of calculus, uh, part two. Um, and we'll talk about part one here in a second. Okay, so any questions so far on the statement here of part two and how we used it in this example that we've been rolling with? So let me know if you're Gucci or if you're Prada. In the chat or in Discord, or how we doing? Is this making sense? Okay, Mr. Hurt is Gucci. Everybody else Gucci, other than it being 8:30 in the morning. And um, so I discovered an interesting bug. You guys probably noticed on my iPad that it says it's 4:41 on Tuesday, January 9th. So whenever I plug the iPad into the computer, the date display changes to that. If I unplug it, it'll display the correct date and time. So I have no idea why it's doing that, but interesting little bug. So, um, okay, well, so let's talk about the second version of the fundamental theorem, or sorry, the first version. Um, and I have to say, first version, second version, this is not standard. So in the particular book that we're using, uh, they call it part one and part two. Um, when I learned this stuff back in the day, my part two is what the book calls part one. So my book that I learned from in high school had this backwards. Whatever. Okay, so the second version asks basically the following: if I have an integral like this, okay, this defines the function of x. Okay, so sort of the idea would be, let's say that I have some function um, f of t, okay, and then let's say a is over here on the left. Then if you pick an x, then so say for example, um, let's say that you pick this x, then that area is this. Okay, but if you picked a different x, like let's say here, then then you would get, in this case, more area, right? So this is a function of x in the sense that depending on what x you pick, um, you get a different value for the integral. And so since we have something whose value depends on x, well, that's what it means to be a function of x. Okay, so does that make sense what this a to x business means? Um, let's make sure we're cool on that before I go on. Okay, so the question is, if I've got a function of x, then I could say, well, what's the derivative of it? How fast is it changing? So what do you guys think that this might be, the answer to this? Okay, so we've got an integral, and then we're going to take the derivative of it. So any brilliant ideas what you think this might be? Okay, so it turns out it's just f of x. Okay, and this maybe isn't too surprising in the sense that, well, if we just said that the integral has something to do with antiderivatives, and the derivative, we know what that is. Well, so what would happen if you took a derivative of an antiderivative? Those two things should sort of cancel each other out, so to speak, right? And so you'd just be left with the original function. Um, okay, so there we go. There's the first version of the fundamental theorem of calculus. Okay, um, and so let's take an example, and I'll show you uh, sort of two methods of computing these, or sort of two ways of thinking about the first version. Okay, so let's actually just use our running example here. Let me define f of x to be the integral from 0 to x of 4 minus x squared dx. Okay, so, or sorry, let me do it 4 minus t squared. Um, the reason I switched to t here as opposed to x is because I don't want to use the letter x in two different ways simultaneously. I technically could, but it's sort of bad form, if you will. Okay, so let's use the second version to figure out what this function is. Well, we already said that um, the antiderivative is this, and then I'm going to write this bar to the right with a 0 at the bottom and an x at the top. And what that means is to plug in the top number, plug in the bottom number, and subtract. Okay? And in this case, the c's cancel, and the second one happened to be mostly zeros, so we just get 4x minus x cubed over 3. Okay. So our function, um, fatty f, is just 4x minus x cubed over 3. Well, what's the derivative of that? Well, it's just 4 minus x squared, which is exactly the function that we started with, right? So it's we started with 4 minus t squared. We just substitute x in for t, and that's it, right? So it's almost too easy. Now, if we had done it, so this would be using the second version. If we did the first version, then we would just say full stop. Okay. Um, Now, the second version doesn't always work. Okay. I mean, in practice, and the reason is, what did we have to do to go from that step to that step? So where the blue arrow is, right? What we had to do was to find an antiderivative. And as I mentioned earlier, that step can be the problem step. In fact, that is the meat of all of these problems. Um, and so we can't necessarily do this by means of the second version, but the first version sort of always does it. Okay. And we'll talk. Let me give you an example of where we have to do it this way, or at least for now. Um, let's say, for example, we had something like that. You guys don't know what the antiderivative of that square root thing is. Now, it is possible to find it, um, and I won't spoil the show, but it is possible to find it, but there are situations where it's not even possible. Okay, so here's another one. Oops. Um, that second one, it is literally impossible to find an antiderivative for it. Sorry. Okay. And so the only way to approach this would be the first version. Now you might say, well, who cares about that second? Who cares about e to the minus t squared? But e to the minus t squared describes basically the bell curve. Okay, so in probability or statistics, when you guys talk about the bell curve, those of you guys who are want to do econ or maybe psych, with statistics and whatnot, then that function is actually really important, and the area under it is actually how you get probability. Um, oh yeah, Dr. Denari. Shout out to Dr. Dunaway. I didn't say Dr. Dunaway until just now. I said Econ. Um, so yes, hello, Professor Econ. Now we're just talking about the fundamental theorem of calculus and um, in both of its versions, and how sometimes you have antiderivatives that you can't actually find, which is annoying. So yeah. Okay, so let me also take another situation. So let's actually go back to, um, well, actually, let me just take the example I just had. So if we asked what's the derivative of, then it would just be e to the minus x squared by FTOC number 1. Okay. Um, all right, so great. Well, let me change the question a little bit. So what do you guys think this would be? So notice what I've changed. I changed the top bound from x to x squared. Okay? So think about this one for a moment. Is the answer going to be exactly the same as what we had a minute ago? Probably not, because I wouldn't be asking the question if it were. Um, but what is it going to be? What do we have to do here? What do we have to consider? Okay, so what's different this time? I mean, yeah, there's the x squared, but all right. So how many of you guys maybe you think, oh, I just have to plug in the thing at the top in place of t, and I get what I get. Okay, so this would be e to the minus x to the fourth in this particular case. Um, is there anything missing? Okay, is that it? Is that it for the answer? Do you guys think that's it? Or do you think there's maybe something missing? And let's not make Dr. Dunaway answer the question. No? No guesses? All right. Well, let me show you what the answer is, and then you guys can tell me why I knew that thing had to be there. Okay, so where'd that 2x come from? Yeah, so I have to multiply by 2x. Why 2x? Where the hell did that come from? Yeah, almost. So this term came because of the chain rule. Okay, so if the x is not just an x, but rather a function of x, then the chain rule applies, and we have to just tack on the derivative of that function, whatever it happens to be. In this case, 2x. Okay, so the chain rule can still apply here, and you guys, have to remember that, unfortunately. Okay, so let's just kind of recap. So the first thing we did was today was the we had previously talked about the left and the right-handed methods, and then we said, okay, well, we could kind of improve them a little bit by doing averaging, and if we average after we do the answers, then that gives us the trapezoid rule. And if we average before we do the functions, then that gives us the midpoint rule. And they're both individually better than the left or the right-handed rules, even though neither of them are perfect. Now, you guys could probably guess there are other methods of doing numerical integration that are even more sophisticated. So there's a method called Simpson's rule, which actually, believe it or not, uses this Archimedes trick and adapts it for non-parabolic functions, which is kind of neat. And that's something that Simpson's rule would talk about in MAT111 for those of you going on. So Ethan, I think you're signed up for 112 with me next semester. Is anybody else going to take Math 112 next semester? If you are, just let me know in the chat or something. I just want to kind of keep tabs on everybody that's going to go on to the next class. Um, okay, and so then the second thing we did was the fundamental theorem, which has sort of two flavors. Flavor number one is what happens when you take the derivative of an antiderivative. And the answer is you mostly pretty much get exactly back what you started with. Uh, and you just may have to use the chain rule kind of thing. Um, and then the second version was to say, all right, we've been computing definite integrals, uh, and we've been interested in those because they represent area under curves. And so, how do we compute those? Well, um, we can compute them by finding an antiderivative and doing some arithmetic with the antiderivative, and that gets us the answers that we're looking for. So like I said, the we had the idea of the derivative, which we talked about early on in the course, as slopes of tangent lines and so on, and that was all great. Um, and then we said, okay, well, if we can take derivatives, then we can think about if I know the derivative, can I know what the function it came from was? And uh, yeah, you can. That's called an antiderivative. You get the plus c, which is a little bit annoying, but we can find those things. Um, and that the integral, which is asking about area, the fact that that has anything to do with antiderivatives is sort of the surprise, and that's why this is called the fundamental theorem of calculus, because it's sort of central to the discipline. But that relationship was definitely not something that you would have just randomly guessed. Um, but it turns out that that's exactly what's true. Okay, so we'll go ahead and quit the stream here for today. Thanks for coming, and please be working on the Edfinity. Please don't put them all off until next week because some of them are a little tricky, and they're definitely not things that can be done overnight. All right, well, I will see you guys on Friday, if not sooner.